Santorini's tranquil beauty has just been shattered by over 2,000 earthquakes in 36 hours. Yet it is what lies beneath that truly terrifies scientists. New data confirms a surge of 300 million cubic meters of magma is rising from the depths, feeding a swelling chamber beneath Colombo that is now over 1 kilometer wide and expanding fast. Authorities rush to understand, is this routine rumbling or the awakening of the very volcano that once destroyed Akrotiri and inspired the Atlantis legend? What happens if this ancient force erupts again? The clock is already ticking. Sirens echoed across Santorini as more than 2,000 earthquakes rattled the island in just a day and a half. Streets emptied, shopkeepers abandoned their stalls, and hotel lobbies filled with nervous tourists clutching passports. The tremors struck in rapid clusters, sometimes 5, 10, even 20 in a single hour, each one feeding a sense of mounting dread. Schools closed without warning. Ferries idled in port, waiting for orders that never came. Local radio hosts fielded frantic calls as rumors spread of cracks splitting roads and ancient walls. Inside the National Observatory of Athens, the duty team worked without pause, eyes fixed on a wall of monitors tracking the swarm. Automated alerts flashed amber, then red. By the 12th hour, seismic logs showed no sign of slowing. At midnight, the observatory issued a rare civil protection watch, an official signal that something extraordinary was unfolding beneath the Aegean. The decision came in under 24 hours, a record for the region. For Santorini's residents, the message was clear. This was no ordinary tectonic jolt. For scientists, the pressure to explain the chaos had reached a breaking point. Inside the observatory, the search for answers narrowed to a single urgent question: what was driving the relentless tremors? The raw seismic data poured in, a torrent of signals from land stations and a web of underwater sensors. But the Aegean is a noisy place. Tectonic quakes, ship engines, even distant storms all leave their mark. Sorting through this chaos required more than human intuition. A new tool took the lead, a machine learning model trained on thousands of labeled seismic events from past eruptions and tectonic jolts. This convolutional neural network, designed by the observatory's data science team, scanned every incoming waveform in real time. With each pulse, it parsed spectral fingerprints invisible to the naked eye, learning to tell the subtle difference between shifting faults and the deep, rhythmic signals of moving magma. The model's precision reached 92%, with an 89% recall, sharply reducing false alarms and missed warnings. When the swarm began, the AI's verdict was unambiguous. The fingerprints matched historic magmatic intrusion, not ordinary tectonic stress. The breakthrough was immediate, but it left a new challenge. If the signals pointed to magma, then imaging the hidden source became the next scientific imperative. Full waveform inversion, a seismic imaging technique likened to ultrasound for the Earth, delivered the first sharp picture of what lay beneath Colombo's crater. The data revealed a tabular intrusion, roughly 300 million cubic meters of magma stalled at a depth of 2.5 to 3.5 kilometers below the seafloor. This dike is not an isolated pocket. Beneath it, at 5 to 7 kilometers depth, sits a much larger mid-crustal reservoir, now estimated at 1.4 cubic kilometers. Over the past decade, this deeper chamber has been inflating at a rate of 4 million cubic meters each year, a slow but relentless pressure that has subtly lifted the caldera rim and caused measurable subsidence on the Colombo seafloor. The precision of these measurements, down to about 100 meters for the dike and 200 meters for the reservoir, comes from the combined power of dense offshore sensors and advanced computational models. The evidence points to a direct hydraulic corridor. Magma is not only accumulating, but moving, linking Santorini and Colombo in a single, restless system. With each passing month, the numbers grow. The pressure builds. What was once thought to be a dormant threat now stands revealed as an active, interconnected network, one with the potential to reshape the Aegean seafloor in ways not seen for centuries. At a depth of 500 meters, the ocean above Colombo acts as a heavy lid, holding back the volatile forces below. But if magma pressure surges past 30 megapascals, models predict a sudden breach, no gradual warning, just a violent rupture. In the first seconds, seawater floods superheated fissures, flash boiling on contact with magma that exceeds 1,100 degrees Celsius. Computational fluid dynamics simulations show the resulting steam plume blasting upward, punching through the water column and erupting into the sky. Under worst-case parameters, that plume could reach 4 kilometers above the surface, carrying sulfur dioxide and volcanic ash high into the atmosphere. The energy released in that instant would send a shockwave racing outward. Most tsunami modeling, using the maximum plausible seafloor uplift, projects a primary wave up to 12 meters tall slamming into Santorini's southern coast. Arrival time, 8 minutes. For any vessel or shoreline within range, there is no time to react. HCMR's lead modeler describes it as a domino effect: pressure, breach, plume, wave, each step fueled by the immense volume of magma now stalled beneath the seafloor. Pressure on the Colombo seafloor does not only threaten an explosive breach. As magma inflates the crust, stresses ripple outward, destabilizing slopes that have held for centuries. Limit equilibrium models, fed by high-resolution bathymetry, identify 3 segments on Colombo's southwestern flank, now primed for failure. The largest, an estimated 0.15 cubic kilometers, could collapse with little warning, its mass plunging downslope and displacing seawater in a violent surge. Marine geochemists at the Hellenic Center for Marine Research have tracked these changes closely, watching as pore pressures rise and the margin creeps closer to the tipping point. The probability of a major submarine landslide within the next decade now stands at 28%. But the threat does not end with the sea. If the magma system breaches, sulfur dioxide and ash could be lofted into the atmosphere, carried eastward by prevailing winds. Atmospheric transport models project that sulfur dioxide concentrations could exceed World Health Organization thresholds for up to 36 hours, producing a toxic haze stretching across the Aegean. For ships and aircraft, this means engine risks and reduced visibility. For islanders, a sudden spike in respiratory danger. Each hazard, whether wave, landslide, or toxic plume, stems from the same restless system, compounding the risks for anyone living or traveling near the heart of the Aegean. Inside the control room at GFZ, a statistician runs her fingers over a series of probability curves projected onto the wall. Each line represents a different simulation, 10,000 scenarios, each one nudged by a slightly different set of assumptions. The numbers are precise, but the reality beneath the Aegean is anything but certain. Full waveform inversion delivers a sharp image of the dike, 300 million cubic meters of magma, mapped to within about 100 meters. Yet even with this clarity, the true volume could be 15% higher or lower. Every parameter, magma viscosity, reservoir pressure, the cohesion of the seafloor slopes, feeds into Monte Carlo ensembles, generating a cloud of possible futures rather than a single forecast. The AI model, for all its speed and accuracy, still produces a 3% false positive rate, meaning that out of every 100 alerts, 3 could be false alarms. The team weighs these margins as they update hazard probabilities, careful not to overstate the threat or lull the public into complacency. The confidence intervals are not just academic, they define the boundary between vigilance and panic, between a necessary warning and a disruptive false alarm. In the world of volcanic forecasting, uncertainty is not a flaw. It is the most honest answer science can give. Beneath layers of volcanic ash and pumice on Santorini, archaeologists uncovered the ruins of Akrotiri, a Bronze Age city frozen in the moment of its destruction. 8 meters of ash entombed frescoes, pottery, and streets, the remnants of a society that vanished almost overnight. Radiocarbon dating places this eruption between 1628 BCE and 1600 BCE. Its violence was enough to collapse the island's caldera and hurl tsunamis across the Aegean. Paleotsunami deposits reveal waves up to 20 meters high striking distant shores. Their force scattered debris far beyond the Cyclades. For decades, scholars have debated whether this cataclysm inspired Plato's tale of Atlantis, a thriving island civilization lost to the sea in a single day and night. While the Atlantis legend remains a matter of myth, the archaeological record leaves no doubt about the scale of the disaster. The Minoan eruption stands as a stark reminder. When the volcanic heart beneath the Aegean stirs, entire cultures can disappear. Maria Lefteriou, from the General Secretariat for Civil Protection, stands over a map dotted with sensor locations and funding figures. The next phase is clear: expand the underwater network before the next surge catches anyone off guard. 8 new seabed monitoring stations will close the blind spots along Colombo's southern flank, each linked to shore by fiber optic cable for real-time data. 12 pressure temperature probes, sensitive enough to catch even subtle hydrothermal shifts, are slated for deployment across the crater floor. The budget, 14 million euros, draws from national funds, European Union research grants, and a matching scheme with local industries. Every euro is earmarked for hard upgrades, denser arrays, faster alerts, and open access hazard maps. The goal is simple: detect trouble early, buy precious minutes, and give Santorini a fighting chance. Beneath Santorini, over 1.4 cubic kilometers of magma now press upward, fed by a surge measurable in millions of cubic meters each year. The same forces that erased civilization still gather in silence. In this moment, the line between legend and disaster grows dangerously thin. What would you do if Atlantis awakens again?